So this is my neural library from scratch, and so first of all you need some extra folders: plots, models, logs, and datasets. This folder you can have anywhere, not just here. So after that, like, this is the main module. Here we have all the functions and classes, optimizers, everything needed is part of the library. So I can show you how it works. So in this requirements file, we have all the packages. You can just pip install all of these. After that, I'll just run this notebook. So you can see the API is just like TensorFlow. Like, we can build a model layer by layer. And the main thing about this is that I wrote this entire project by my own hands. Like, I didn't use AI to generate the code. So this is a simple data set where the first two columns are voltage levels, and we are implementing an AND gate. So, like, any both of them are higher than 0, then the target is 1. Any one of them is 0, then the target is 0. So we have batch size as 1. Rest of them are just variations on the batch size. So I'll just run this one. So it shows the weights and biases. So it's a simple model. It's just an input layer, one hidden layer, and then the output layer. So we are training it. So you can see we are getting really good accuracy. And this is the confusion matrix also. So we saved the history, and then we predicted on the test set. We got 99% accuracy. This was the incorrect prediction. So we saved the weights also. And then the extra feature of this library is this plotter. It references the saved training history from the logs, and it can plot different kinds of graphs, such as the gradients. So the index 0 means this is the first layer, weights and biases. This is the second layer, weights and biases. So how much was the gradient for the first 4 elements of the weights matrix per update? Just the first 700 updates. Actually, like, we might have like 7,000 updates, but we are just showing first 700. And then weights and bias values, the actual values for the weights and bias elements, how they vary across updates. And then the loss and accuracy, loss and score, and then the confusion. So one other thing we can see is the risk with ReLU. So, like, we know ReLU is 0 if the input is negative, and it is the input itself when it is greater than 0. So uh, this can lead to vanishing gradients. So, like, the weights won't be updated if the input is less than 0. So, like, here I am putting some custom weights. All of them are negative. So the output, so I know the output of this, the first layer, will definitely be negative. And so if I train it, We can see the accuracy doesn't go above 50% and no change in the confusion matrix also. True positives are 0, false negatives are 100. So we save the history, we save the weights, and then now let's see the plots. We can see there was no gradient at all for the first layer and for the second layer's weights also. Just the final bias was oscillating up and down because whatever learning this thing was getting, it wasn't propagating to earlier layers, so it was just oscillating up and down. And the weights and bias values, they remained static, all of them, just the bias was shifting in a pattern, so it never converged to any value. And we can see flat graph for the metrics also. We predict it will be, yeah, so many incorrect predictions. Then the solution is leaky Rayleigh. So in the negative side, instead of 0, we have a little bit of a slope, which is the leak, 0.1. Once again, I'm putting the same negative weights for the first layer. And now let's see. Accuracy comes to 70%. It's getting trained. %75. And on the plots, you can see we found some gradients. The first layer as well, everyone found some gradients. And we can see the values are shifting. Time. This bias is actually going down, so it's like a stable gradient. And the metrics are also better here. %77 on the test set. So now we can also plot the predictions over time. So I'll just load the earlier saved model without the negative weights, the random weights. So we can visualize this. So 0 and 1. So only if either input is 0, result should be 0. So red, we should find red only on the x-axis and the y-axis, not anywhere in between, anywhere in this area. We can see that it's improving over time. Now one more thing is the loss landscape. So after the model has been trained, we can see the loss landscape, like the valleys and hills that they talk about of the loss function, where our model is in that landscape. So this is a contour plot. It's a 2D plot of a 3D area. So like if a hill is there, the top of the hill is darker or lighter than the base of the hill. So this has 4 grids, so 2 of them are done. It takes some time to generate because it's a very heavy computation. Yeah, this is how it looks like. Our model is at the center, alpha and beta 0, 0. Alpha and beta are slight modifications to the weights vector of the model. Like if the weights of the model were slightly here or here or here, the model would be there. So like the black color here is the value of the loss function. So we should be in the black region. This is the loss. The loss is increasing the more we move further away from where we currently are. So that means the training was successful. So the plots are saved in this folder, models and logs. So this is a data set I took from Kaggle. Because this is more complex than a simple AND gate. So we wanted to see how it would perform on like a proper Kaggle dataset. Here also we are doing binary classification. I don't know what this error is, but it's working. So this is just pre-processing. So now we have a more complex model. We have 7 input features. This is just a random seed, 5. Then we have 3 hidden layers and 1 output layer. So we'll train it. So we got 85% accuracy. So I have already trained it in the past, so I know that only 20 epochs are necessary to get here, and after this it doesn't improve much. So I saved the history, and now we already know gradients, weights and score, how the graph looks like. So here is something different. So I first just standardize the test set from the same means and standard deviations taken from the train set. Then predicting 86% accuracy, it's good. Then now I also implemented PCA, principal component analysis. So what it does is it, like if you have more than 2 features, like you have 7 features and you want to plot it on a 2D plot, you have only 2 axes. So it combines and transforms the axes so that the spread between the data points, this Casimir, this is the target name. So the spread between these points is maximized. There is an algorithm for that. I just implemented it. So it gives us the new axis and then we can plot this new axis. This is how it looks like. 0, 1 and incorrect. So by chance, this is just the first 200 samples. By chance, all the zero ones are only incorrect. Otherwise, if I shuffled it, some blue dots also would be crossed. So this is just by chance that all the red ones are incorrect. So we can see that they are decreasing with the epochs. So one more thing, regression. So everything is the same as classification, just that We are now predicting a continuous value target. So here, yeah, here we have a different metric called R square score. The closer it is to 1, the better it is. So we can see it improved a lot in just a few epochs. Eighty-four, 0.84. R square score, it's decent. Then so this we've already seen how these plots look like. There's no confusion matrix for regression. Okay, 81, 0.81 on test set. Then same we are doing PCA, but now we need only one axis for the features because the second y-axis will be the target. So this plot looks different than the classification plot. The blue ones are targets and orange crosses are predictions. So we can see they are overlapping. Like if you see this dot, this distance, this got decreased so far. So now we can go into the. So this is just some data set utilities. This gets us the AND gate data set using NumPy, get mini batch. All these things I have to write to implement the training algorithm, standardize the data. So I didn't even use scikit-learn. So my goal was to see if I can go a little bit, like the ML abstraction was too high. So I was thinking of going a bit low for everything. So yeah, that might be a bit silly, but that's what I did. So equalizing classes. So making sure all the samples, like equal number of samples are there for every class in the dataset. Then splitting the classes, splitting the regression data. This is PCA. So I referenced a blog. There are some good blogs there. So that show everything like eigenvalues, eigenvectors. They have the entire algorithm. I went through it, I understood it, then I implemented it here. Transpose and everything. We had to make sure all the dimensions are correct for the operations like dot product functions. Here are just np dot vectorize means like if to this function x is a numpy array, then this is calculated on every element of x. That's what vectorize does. So this is like activation functions and their derivatives. We need it for gradient descent in the backward pass. Then these are loss functions. For the output layer, first calculating the loss, then derivative of the loss, then the error in the output layer. So like MSC was the base class because everything has roughly the same thing. So binary loss is just overriding these two. Error output layer is common for everything, for every loss function. I only have two of these here. This is not fully working right now, categorical loss. Then this is what makes the TensorFlow like API. We have a layer which has neurons, activation function, its derivative. These all these variables after which we have underscore. So like there's a really good article. So I reference this article. So this article uses these notations. So there are four fundamental equations behind backpropagation. These all. So these are the notations. Like this is del and A and sigma. So I use these here. So I just put an underscore. Like this is what I used in my notebook on pen and paper to practice. So I know what these are. Then it has some functions as well. Polylayer, this like allows us to have different activation functions for different neurons in the same layer, but this didn't give any improvement in accuracy. So weights, it's also a separate class. So like between every two adjacent layers is one matrix of weights. So it takes the two layers as it in its constructor and saves that. So we can initialize it using he initialization. So it helps if we are using ReLU functions. So it's like it samples the waves from a standard normal distribution instead of totally random. Then this is the main model class. It has layers and weights and the loss function and a seed. In most places we have a seed, so it's reproducible. We can add layers, we can compile it. Compiling it will initialize the layers and the weights. Then this will give us the elements, some other utility functions, save the weights, load the weights. These are optimizers. So the simplest one is SGD, the standard gradient descent. So the way this is structured is, so this gives us the gradients and the errors. On pass is executed after each pass is over. So in future, and also we can update the weights and biases so that future optimizers, they can just extend this like momentum. Yeah, so like SDD is the base class for the optimizer. Many of these methods we can just reuse. So momentum requires us to store some previous values. So we have some new, we're defining some new variables in the initialization function. This is not the constructor, but we need to call set model anyways. So I put these lines here. So in update weights and biases, we are multiplying it with the momentum term. We're updating the momentum term and then adding it to the layer index. Then I implemented RMS prop also. Adam wasn't working as of now. This is matplotlib. This plotter class is fully in that. So it reads the log file. Then we have all these functions, plot gradients, plot weights, all of these big functions. Each of them is like 50-60 lines. And it looks like most of the code is the same, but at the time I didn't know how to like separate the similarity out into one central location and then use it. I did as much as I could, but yeah, it's still every function is still like 70 lines. Then we have trainer. This also has like main functions here are backward pass and forward pass. Then it updates the weights. Update passes just forwards the call to the optimizer. Update weights also. Then we can save the history. The main function, which is train, takes features, targets, batch size, learning rate, epochs. This is how many epochs to log. If you log, you are training it for like 500 epochs and you log all of them, the size of the log file becomes very large, like 2 GB. So you can limit that and get the confusion matrix, accuracy, then predict. Regression trainer just extends this. Some minor changes need to be made, like R square score instead of accuracy. This is the only reason we have regression trainer. Just we are just overriding the predict method. Then this is the logger object. Just make sure we are following a file format here. This is the format. So the logger just has a dictionary in which it follows this format, and every step of the training is according to the format. It is first written into the dictionary in the memory while it is executed, while it is being executed, and after that we can, when we say write log, it will just dump that into a JSON file, and then it will reset itself. So that's it. So this was my college major project also. So most like I did all the coding by myself. My teammates helped me gather the data sets and some other report work. Yeah, so that was it.